All right, so while you were doing this page in the notes, there were a couple questions we did not quite finish in there, did not do. But, listen, I'm sick. We got to slow things down a little bit. Might as well go over 39, 40 basically did, and 41. So just to make sure you're comfortable. So up here you notice there's a mass given to you. There's an initial velocity. Well, you can just say v for now. Thin out this marker. Now there's another v over here. So if we had one earlier, we can call that a vi, an initial velocity. One later, there's a vf. They put a positive in front of each just to insist that they're both going in the same direction. And they ask for delta p. Okay. There's more than one way to skin this cat. However, there's definitely one way that's quicker than others. So if your givens are m, vi, vf, and delta p, I mean, the quickest thing to do over here, I'm saving us a little time writing them, but you guys can write faster than me, I think, with this mouse. Delta p is, if we went back to that page in the notes when we first introduced momentum, worth restating here. There's a little box that we called easy. And it's not necessarily easy to remember to do it. It's easy, though, in that it's easy to convert your basic reference table formula, P equals mv. These are vectors, momentum, and velocity. Mass is a scalar. It's easy to actually say, okay, well, what if we want the average momentum? Well, mass is not changing for our problem, so that would just be mass times the average velocity. If we wanted the initial momentum, it would be mass times the initial velocity. If we wanted the final momentum, it would be mass times the final velocity. And as you see over here, if you want the change in momentum, it would be mass times the change in velocity. So these are easy, what we call single object adjustments to the momentum equation. Now you got to be careful here. If you have a single object that then explodes into two parts, you got to pay attention to what you're doing here, especially this one down on the bottom. That becomes an explosion, a conservation of momentum that you just worked on recently. Anyway, knowing this, the easiest way to deal with this problem is, of course, m delta v. And though you don't have delta v written over here, you should remember your deltas. Delta is always final minus initial. So m v final minus v initial. And that is the easiest, most direct way to solve this problem. It's important to recognize the sign on this. So when you substitute and solve, and again, I'm being a little lazy here with the givens, but when you substitute and solve, you're going to have your mass, which is 2,000 kilograms. And I'll write my units right here. Be a little thorough. 2,000 kilograms. And you have to go in the correct order. VF minus VI. VF is 15. It's not 25. It's not just big minus little. It's final minus initial. 15 minus 25. And naturally, you will see here this will come out negative. This will be a negative 10 times 2,000 is negative 20,000. That negative does matter. What that's telling you is that the change in momentum, which is a vector, is in the opposite direction of the motion. So the motion was in the positive direction. The change in momentum is in the opposite direction. And you may say, well, who cares? Who's keeping track of change in momentum? Actually, this becomes a more useful concept when you recognize that impulse, which is a vector, is change in momentum. Which then means that impulse here is going to be negative. And if you further look at your reference table and see that, let me change the color up once more. If you further change up, the impulse will be exactly, I don't even need to put just negative, negative 20,000. If you look at one other relationship we have in that same equation in your reference table, impulse is also, the first part of the equation, F net t. F net, that's a vector, t, for time. Sometimes they call it delta t, in our reference table just t. And so if the impulse is in the negative direction, well then the force, which is also a vector, must be in the negative direction as well. And so you know the only way that this happened, and it all comes back now, the only way this car is going to slow down, if it's moving forward, is if it, let's see, if the car is moving forward, the only way it's going to slow down is if it experiences a force in the backward direction, a net force. This was the velocity. And of course that makes sense. You got to have some kind of braking force. Okay, number 40, you had left off with the substitution from F net t, and you substituted F net as ma times t. It's an easy thing to plug in, of course. Here's your mass, here's your acceleration, here's your time, you get the impulse. Just to repeat, do not be afraid of what appears to be very large accelerations. This magnitude of acceleration seems unreasonable, and that's only because you conflate acceleration with speed or velocity. The tennis ball is not traveling at 18,000 meters per second. It is changing velocity at a rate of 18,000 meters per second each second. It gets away with this because it doesn't last for a second. The collision lasts for 4/1000ths of a second. And so, though if it lasted for a full second, it would go perhaps from 0 to 18,000 meters per second, it only lasts for 4/1000ths of a second, which means it only changes velocity by 4/1000ths of this velocity, this acceleration right here. And so it is reasonable because of the short time. Last question right here. Bobo. You know, sometimes they throw a trick question at you. It's not really a trick, but they want to catch you slipping. Here's the mass of Bobo. I'll put a little MB. He's riding his Huffy. That's a bike, by the way. And yes, the bike also has a mass. I'll put MH. Huffy is an old brand of bike. Here's the velocity. Here's, now they tell you Bobo and his Huffy have a combined momentum. There's the momentum. Determine the mass of the bike. So the mass of the Huffy. And so here, this is no different than that little adjustment we were making. So we have the mass of Bobo. We have the mass of the Huffy. That's our question mark. We have the velocity of, who is this? This velocity actually is of both of them. You could say velocity of Bobo. You could say velocity of Huffy. You could even say velocity of Bobo and Huffy together. All of these are 10. It's all moving together same. And because we read north, sorry, I'm not yelling right now, north is going to be positive here. That's the easiest way to do it. And they also gave you the combined momentum. Now, I wrote all three of these out over here because the combined momentum, that's the momentum of Bobo and the Huffy. They gave you that to be 800. That kind of tells me, oh, wait a minute. This reminds me of that easy box we just did. That easy box allows these sort of simple adjustments. You know, the easy momentum box. And this is just coordinating your givens. So let's see. Momentum of Bobo, of course, is going to be the mass of Bobo times the velocity of Bobo. The momentum of the Huffy, same thing. How about the momentum of Bobo and the Huffy? Well, that's going to be the mass of Bobo and the Huffy times the velocity of Bobo and the Huffy. So you make these simple adjustments, these easy adjustments to the basic equation, the reference table, and you got a lot of options. This is going to be the one that applies here. And so, if I'm looking for, since they gave me the momentum of Bobo and the Huffy, it makes sense for me to do the mass of Bobo and the Huffy times the velocity of Bobo and the Huffy. By the way, this is not the only way to do this problem. There are other ways to do it, but this is pretty straightforward. And so when you substitute and solve this, you know that 800, you don't yet know the mass of Bobo and the Huffy. You know only the mass of Bobo. And the velocity here was 10. And when you solve this, obviously, the combined mass is 800 over 10, or 80 kilograms. Now, it's a very easy subtraction to recognize that if it's the combined mass is 80, and Bobo's mass was 70, well then clearly the mass of the Huffy has to be the remaining difference there, the 10 kilograms. Again, you could have gone at this other ways. You could have done the momentum of the Huffy only is mass of the Huffy only times velocity of the Huffy only. That would have worked too, but you would have had to first figure this out. Now, the way you would have to figure that out is very similar to what we just did, but in reverse. So you would say, well, the momentum of Bobo and the Huffy is actually the momentum of Bobo plus the momentum of Huffy. That's the way momentum works. We did this actually in conservation of momentum. You have to add them. Momentum sums. It's a vector sum, but these two are moving together, so you don't have to worry about different directions. And so this one was 800 equals, well, the momentum of Bobo you could easily figure out would be mass of Bobo times the velocity of Bobo. I know this font is not great, my writing. So listen to the words. And mass of Bobo is 70, velocity is 10. So that would be 700 plus momentum of the Huffy. Clearly that's 100. And so if you were to do it this way, you would have had 100 equals the mass of the Huffy times its velocity of 10, and you would have gotten 100 divided by 10, 10 kilograms either way. So again, more than one way to skin a cat, but notice what I'm doing here. Both in question 41 and in question 39, that easy box, I'm really taking the time to coordinate my givens. The givens are everything here. The math is a piece of cake. You have to set up your givens properly. All right, that's good on that.